In the last class, we had seen how to evaluate determinant of a matrix of order 1, 2 or 3. Today in this class, we shall be discussing properties of determinants. Now here the properties of determinants I am going to explain with an example. So let us take a matrix of order 3. This is the matrix. The determinant of this matrix is represented like this and is evaluated along the first row where this element will change its sign. Minus 2 into 2 minus 9 plus 3 into 4 minus 3 minus 5 plus 14 plus 3, which is equal to 12. So what we are getting here is determinant A is 12. This is the initial information we have. So let us start with the first property. The first property says that if all rows and columns of a matrix, obviously a square matrix, are interchanged, the determinant does not change. Now when we are saying that rows and columns interchange, that means this interchange has to happen in the correspondence. So first row will change into first column and likewise. So this is the initial matrix A. If we find out the determinant of the matrix after interchanging rows and columns, that means the first row is first column, the second row is second column, and the third row is third column. So it is important to note that the first row changes into first column only and not the second column. So now if we evaluate again along the first row, this element will change its sign and we have expression like this: 2 minus 6 plus 3 times 6 minus 3, which is minus 5 minus 4 plus 8 plus 9, which is again 12. So you can see here initial determinant had a value equal to 12. When the rows and columns have been interchanged, the determinant remains the same. Alright, so the initial determinant is this. The determinant which we have obtained here is basically determinant of A transpose. You must be remembering that transpose of a matrix is found by interchanging rows into corresponding columns. So we get this important property here: determinant of any matrix is same as determinant of its transpose. The second property, if all elements of any row or column are zeros, the determinant is also equal to 0. So if we have a determinant where suppose the second row is all 0 like this, now you know to evaluate the determinant, suppose you want to expand along the second column, since all elements are 0, the resultant will be a 0. So two important properties we have dealt. The third property, now when we were finding out the inverse of a matrix, we discussed the row and column operations, and we know there are 3 row operations and 3 column operations that can be applicable to a square matrix to find its inverse. Now those row operations, suppose we are using row operations. So if we have a row operation of this kind, any 2 rows are interchanged, in that case we will see what effect does it bring to the determinant of the matrix. So since we are interchanging first and second rows, so like this. Now let us find out the determinant again along by expansion along the first row. So 2 into 2 minus 6 minus 1 into 1 minus 9 plus 3 into 2 minus 6. This is minus 8 plus 8 plus 12. So the result is 12. So you can see here, if any two rows of a matrix are interchanged, the determinant does not change. The same thing applies to a column also. If any two columns of a matrix are interchanged, in that case the determinant does not change. The other kind of operations, row operation we have studied is, suppose we are making changes in row 1 as twice of R1. In that case, the determinant, first row is multiplied by 2. Here is the first row, multiplying by 2, we get 2, 4, 6. The second row and the third row remain the same. Again, evaluating by expansion along first row. So we get 2 into 1 minus 6 minus 4 into 2 minus 9 plus 6 into 4 minus 3. So on further simplification, this value is minus 10. Here is plus 28 plus 6. So this 18 plus 6, 24, which can be written as 2 times 12. Now where did this 2 come from? This 2 has come from here, the constant by which we have multiplied elements of row 1. So here if any row is multiplied by a constant, the determinant also gets multiplied by the same constant. The same concept applies to columns also. So in case we multiply the third column elements by minus 4 and evaluate the determinant will be minus 4 times the initial value of determinant, which is 12. The third kind of row operation is something like this, where changes in R1 can be done with respect to changes in R2. So the new determinant that we obtain here is, from here adding R1 and R2, we get 3, 3, 6. The second row is same and the third row is same. Once again evaluating along the first row. So 3 into 1 minus 6 minus 3 times 2 minus 9 plus 6 times 4 minus 3. So this is minus 5 minus 15 minus 7 plus 21 plus 6. So 27 minus 15, 12. So here we notice that the value of determinant is again the same. So we have studied 3 row operations. Let us quickly see what effect do these row operations bring on the determinants. So if we interchange the rows, the determinant remains the same. If we make changes in any one row by multiplying it by a scalar, the determinant also gets multiplied by the scalar. If we perform this kind of an operation where changes in one row are brought about with respect to corresponding elements of some other row, in that case also the determinant does not change its value. Now the same concept applies to columns as well. So in the next property, let us find out determinant when the matrix is multiplied by some constant. So here we need to understand that this is scalar multiplication. Scalar multiplication means that all the elements of the matrix are multiplied by the same scalar quantity. So we are finding out here determinant of twice of A. So multiply each element by 2. The first row is 2, 4, 6. Second row 4, 2, 6. And the third row is 6, 4, 2. Evaluating by expansion along first row, 2 into 4 minus 24 minus 4 times 8 minus 36 plus 6 times 16 minus 12. Forming this calculation, this is minus 20 minus 40 minus 4 times, this is minus 28 plus 6 into 4, 24 minus 40 plus 112 plus 24. Again simplifying, we get, which is equal to 96, and 96 can be written as 8 times 12, and 8 is 2 cube. So where did this 2 come from? 2 comes from this constant, by the constant by which we have multiplied A. What is this 3? This is the order of the matrix. So order of this matrix is 3. So in general we can write down that if we are multiplying a matrix of order 3, say order n, by a scalar quantity k, we shall be getting k to the power n multiplied by determinant of the matrix of order n. So this is one standard result which is obtained. Now here, please understand, in this case we have multiplied each row of the matrix by 2. In one of the initial operations, we were multiplying one of the rows by the constant 2. Here we have done scalar multiplication, expanded the matrix, expanded the determinant. We are getting 2 cube times 12. 2 is the number by which we have multiplied the elements of the matrix. 3 is the order. So generalizing, we get this result. The last property is, if we have a determinant this way, the same determinant that we have taken, and suppose the elements of the first row are this, first column. The elements of first column have been changed. So this, if it so happens that any column or any row has elements which are expressed as sum of 2 or more terms, in that case the determinant can be expressed as sum of 2 determinants. In this determinant, the second column is 212, third column is 331. Here also the second column and the third column remains the same. The first column with elements 1, 2, 3 written here, and the next elements A, B, C written here. So this way the determinant can be expressed as sum of 2 determinants. Let's make a small change here. Suppose the elements of the, not all elements of first column, say only one of the elements is written like this, and 2 elements are expressed as sum of 2 terms, and this is the determinant. In this case also, we can express the determinant as sum of 2 determinants, where once again the second column and the third column remain the same. So here is only 1. You can write down 1 as 1 plus 0. Write down the elements 1, 2, 3 in the first column here, and the elements 0, B, C like this. In case we have a determinant where suppose the first column is written as sum of 3 terms like this, then because the first column is expressed as sum of 3 terms, the determinant can be expressed as sum of 3 determinants. In these determinants, the second row is the same, the third row is also the same, the first row in the first determinant will be the first set of elements 1, 2, 3, then take the next set of elements A, B, C, and the third set of elements B, C, D here. Here it has to be remembered that this property can be used only for one row at a time or one column at a time. So these are some important properties of determinants, and now in the next class we shall be using these properties to evaluate the determinants.